everybody. Welcome to this session. Thank you all for joining us. So this is, my name is Sherry, and this session is called the There Goes That Boom Boom Pow session at the Earth Institute for the EI Live K-12 session for students and educators. For those of you who aren't familiar with the Earth Institute, the core mission is to foster greater understanding of the science behind climate change and sustainability and what we as global citizens can do. Experts that make up the Earth Institute include economists, business and policy experts, specialists in public health, and earth scientists. The Institute is made up of more than 24 or so research centers and several hundred people who collaborate across many different departments and disciplines at Columbia University. So what we're hoping to do with these EI Live K-12 sessions is to introduce you all to our interdisciplinary work through our scientific experts. So we are going to have these weekly sessions until the end of June. And if you all would like any more information about the upcoming sessions, please don't hesitate to contact me directly. And so today we're very lucky to have Nicholas Frierson with us from the Lamont Doherty Earth Observatory. He is going to be speaking to us about volcanic eruptions and what scientists are doing to predict those eruptions. And so Nicholas researches how to anticipate volcanic eruptions in real time, among many things. And so he'll be sharing some of that research that he conducts at Lamont with us today. And what is Lamont? So that's where Nicholas works. And Lamont is the largest piece of the Earth Institute, and the fundamental and basic science research within the Earth Institute is all based at Lamont. It's a very important research entity, and it's a part of Earth Institute at Columbia. And so Nicholas will share their presentation. And at the end of that presentation, we have someone from NASA GISS who will come and share some resources with us all, which will be great. So take it away, Nicholas.
Okay, well, thank you very much, Sherry, and hello, everyone. Yeah, my name is Nick Frierson. I'm going to share my screen with you. I'm at Columbia University in New York, and let's see, get that working. And let's start that. Here we go. I changed the title very subtly, you might see there. It said Boom Boom Pow, and I thought this was much more of a wow factor, so I called it that. But the thing is these are volcanoes are amazing things, and particularly hard to predict what they're going to do. I'm an engineer at Columbia University, and I'm going to talk today about volcano monitoring and the move towards anticipating and maybe predicting eruptions, which is no mean feat. I work with a number of people. One of them, Einat Lev, she's a volcanologist at Lamont Observatory, mentioned on the screen there. This is her daughter, by the way. So I put this amazing picture up first because basically, you know, they went. This is I have to say, Fagradalsfjall volcano in Iceland, and I know I completely messed that up. But it's erupting at the moment. It started erupting a few weeks ago. And it's a very small volcano, and you can get quite close to it. And it's quite interesting to be able to do that and see it erupting like this. But not all volcanoes are actually this passive, if you like. And so being able to predict what some of the ones which have much more consequential effects when they erupt is something that's very important to us. So basically, Iceland and that particular volcano sit on the Mid-Atlantic Ridge. Now, for those of you who don't know, the Mid-Atlantic Ridge is this red line that runs up the middle of the Atlantic Ocean between the Americas and Eurasia, basically, and it forms the separation of two plates, and the two plates are moving apart. They're called a spreading center. And Iceland sits right on that spreading center. So it's kind of a huge crack in the ground where many volcanoes and lava can form, magma can flow up to the surface. It's quite a fascinating place. Now today I'm mostly going to talk about work that we're going to do this summer, but I want to touch on some, maybe more well-known volcanoes like Vesuvius and something, things that they've done in the past, obviously, which can be pretty devastating. And then this is where we're going to be working, the Aleutian Islands. We're going to be working there this summer. And the Aleutian Islands are basically a volcanic arc. So they're a chain of islands that go between Alaska and Russia, basically. And they're on the edge of a plate and a boundary. And form a big chain of active volcanoes, which not many people know about. We'll be talking more about those. Let's see. So yeah, so just touching briefly back on Vesuvius again. So Vesuvius is a volcano in Italy. It's very close to Naples, across the Naples Bay, basically. And you know, it looks very serene right now. But you know, as I'm sure many of you know, back in AD 79, this volcano erupted and sent scorching clouds of rock and gases down the slopes, and basically engulfed the Roman towns of Pompeii and Herculaneum. I'm doing well on these today. And basically, I mean, they killed a couple of 2,000 people or so with that eruption. But actually, quite a few of them got away. And I think if they'd had an early warning system, which in Roman times would be something, I mean, they thought the gods lived in the volcanoes then. But if they did have an early warning system, they would have been able to get more people to safety. So here we have the two volcanoes that I'm going to visit this summer in the Aleutian Islands. You can see on the map, here's part of that Aleutian Island arc that I was talking about. And here's this volcano called Okmok. And here's a second volcano called Cleveland. Okmok is the one on the left of the image here. And this is a large caldera. Okmok actually erupted, again, very explosively in Roman times. So I had a hard time of it in Rome with all the volcanic activity going on. Now, this is a long way from Rome, but they're thinking now that the amount of material that it threw up into the atmosphere actually affected things like crops in faraway places as Italy, and had potential effects on hastening the downfall of the Roman Empire. This is Cleveland volcano, the one at the bottom of the image. Absolutely classically shaped volcano in my view. There's a small crater at the top, and basically has quite regular emissions of rocks and ash, which pour down the flanks and keep growing the volcanoes to keep this shape. And in fact, it erupted as recently as last summer, June 2020, so about a year ago, and through a dust cloud up to about 20,000 feet. Now, you think, well, hey, these are in the middle of nowhere, so they don't really affect anyone. But actually, this island arc is right in the line where a lot of air traffic goes between, the west coast of America and Asia, and that's a really heavily trafficked route. And so, a big ash cloud like this has a big effect. So being able to predict when these things are going to happen can save lives and save money, basically. So how do you go about predicting volcanic eruptions? Well, there are some dangers and risks involved with monitoring volcanic eruptions. This is about the most risky picture, I think, or a risky group of people that I've seen who are trying to monitor volcanic activity. This is quite an incredible picture. But how can we understand more about a volcano so that we might forecast the future eruption? Well, this is a big problem, and so to solve any big problem, you really have to break it down into smaller bite-sized chunks that you can actually get your head around. And once we have understood and nailed those little separate items, you can start to build them back up together into some multi-dimensional system that we can actually start to understand. And it is a big problem. But the proof is in the pudding. So the best way to test our ideas is to monitor a volcano before, during, and after an eruption. And sounds simple, but then what we would, once we have the information, the data that we collect before, during, and after an eruption, then we would attempt to hindcast the eruption. Now, what that means is that all that data that information that we collect before the eruption, we can feed that into our models, our computers, and they chomp away on the data, and we let them run without telling the computer programs, the simulations that we're going to do, that there's actually an eruption going to happen. And we try and evolve those programs to see if they can actually determine that there will be an eruption before it actually happens. And if we can do that, then you have some security in applying that kind of idea to a volcano that hasn't actually erupted yet, and see if it can predict when it's going to erupt. And that's the sort of thing that we're hoping to try to do. So if we're going to do that, we need to measure some things, some parameters about the volcano, some things that it's doing, so that we know what, we can look at those things that it's doing and sort of see if there's any patterns to them. And so we can measure earthquake activity or seismicity. So basically what happens there is that as the volcano starts to become more active and magma starts to push up towards the surface, it increases the volume nearer the surface, and it's starting to push its way through the base of the actual volcano that we can see, and it starts to shatter the rock around it. And this is one of the main things that causes the earthquakes that we can record. And so we can, if we put seismometers, these things that measure the vibrations in the ground around a volcano, we can see the activity. And if the activity starts to increase, then you might think that something is going to happen. The only problem there is, because it says, hey, well, problem solved. But actually, the only thing there is that there isn't always a lot of warning when an eruption happens. Sometimes these things just well up really quickly, and you get almost no warning, which is, so you need some other kind of precursors, as they call it, some other ways of understanding what's happening with the volcano over time. And so we can measure the change in shape of the volcano. So what does that mean? Well, basically, when that same magma is welling up and filling the chamber in deep in the ground beneath the top of the volcano that we can see, it will actually change the shape of the volcano itself. It'll force it upwards, it's like a pressure cooker, and it pushes outwards. And the volcano changes shape, even if it's very slightly, initially anyway. And so we can look at for things like that. So this is Mount St. Helens, which erupted in 1980, in Washington State. And before it erupted, a large bulge started to appear on one of the flanks of the volcano, and then it erupted out from that side and blew out the whole side of the volcano. So, you can see that is quite a promising way of looking at changes in a volcano state. But it's maybe still very close to the time when it's going to erupt. However, if you can measure tiny little changes over time, that we couldn't even measure ourselves, just by looking at it, using something like a tilt meter, like you can see in the on the slide here. These can measure, parts per million of angle change, basically. So if you imagine that tilt meter that is bolted into the ground on the side of the volcano, the volcano moves a very tiny bit because the whole thing's expanding a little. You can actually measure that tilt of that machine, and you can use that to, over time to see some sort of progression. And so we have another instrument then. We have a tilt meter. We're measuring deformation, basically. And as it says here, if we can measure a part per million, well, what does that mean? Because it's like, what's a part per million? Well, it's like having this 1 kilometer long, plank. And so that's 1,000 meters, yeah? And then 1 meter has 1,000 millimeters in it. So there's 1 million millimeters in a kilometer. And so if you have 1 million millimeters in a kilometer, then you have a 1,000,000-to-1 ratio. So if you lift the plank up one end by 1 millimeter, and the plank's a kilometer long, you've got a 1,000,000-to-1 ratio. So you can see how sensitive these things are. And they need to be as well. We can also measure changes in the shape of the volcano just with GPS receivers. So if you bolt down a really good GPS onto the side of your volcano, then if the volcano changes shape, the whole GPS moves a little. And if you know the position of the GPS to within a tiny fractions of an inch, you can actually see it moving over time. And so you can use GPS as well to measure deformation. And we can even do it from space. We can actually use what's called satellite interferometry, which is something that's a whole subject in itself. So we won't spend any time on it now, but you feel free to email me or whatever about it if you want to. But it's a way of seeing changes to sort of large areas of deformation, which is very handy as well. Another thing we can do is we can measure subsonic sound waves coming from the volcano. Yeah? This is called infrasound, an infrasound measurement. Now, what is infrasound? Well, infrasound is as simple as, you see the little picture there, this little boy blowing on the top of a bottle. I'm sure we've all done it. I've done it. And, you know, if you do it just right, blow across the top of the bottle and you create a resonance in the volume above the water, say, in the bottle, and it produces a tone. And if you drink a bit of the water and do it again, the tone changes and actually drops a little. And conversely, if you fill the bottle up a bit, the tone goes up when you blow on it. Now, it's the same with a volcano, because of this huge, you know, sort of hole in the ground in the middle of the volcano, which has a certain shape. When the wind blows across the top of it, and it's always pretty windy on the top of volcanoes, then you can get this resonance occurring. And because it's such a big thing, the frequency is so low, we can't actually hear it, which is why it's called infrasound. And so we can measure that. And in fact, it says in the bottom right-hand corner of the slide here, there's a little graph, and it shows this sort of colored spike. And that was a peak in some infrasound signal that was recorded on Cleveland volcano, where we're going this summer, on the 21st of July, 2015, at a station which was 2.5 miles from the summit of the volcano. And yet it did a really good recording of some kind of explosive signal that went on there, which is really, really cool, because it means you don't actually have to have the instrument right sat on the sort of the top of the volcano where it's likely to get damaged or burnt to a crisp or something like that. So we're very, it's a good methodology, and a number of scientists now are really taking this to another level, measuring volcanic activity. What else can we do? Well, is there anything else? Yes, actually, we can measure the gases that come out of a volcano. And they're proving to be very key, I think, in the future of volcano monitoring. We can measure things like carbon dioxide emissions and sulfur dioxide and a number of other gases as well. And particularly what we look at is the volume of the gas being emitted and the ratio of the gases that are coming out. Because down deep in the volcano, you've got the magma chamber, or the areas of magma, and when they become heated up and more active, they rise, they get less dense and they rise, and then they're releasing gases. And so if you start to release more and more gases, you know that something's happening. And I think, and then this is an art again in itself, and scientists study this in great detail, and the ratio of these gases can become very important. So if we can just monitor them, we can just measure them, then and get that data back off the volcano, then people can start working on it and start trying to predict what's going to happen. Some of these gases, you know, are not very pleasant apparently, which is not surprising if there's sulfurous gases and things like that. So, but when get to go to these places, you get these amazing places. These are colleagues of mine and scientists around the world, you know, sitting on the top of these incredible volcanoes, measuring the gases, measuring all sorts of things by the looks of it, and having a great time and getting fantastic data. Now, the thing is that we hope that we don't have to be physically there all the time, so we can set our instruments up and then go away and get the data sent to us, which is something that we think about. So we've just been going through talking about all the different sensors that we can put onto a volcano. And so have we actually thought of everything? Well, I would say the one thing we haven't mentioned yet is actually heat. Funnily enough, volcanoes produce a lot of heat. But when they're actually in a state of not actually erupting, they may not appear to be emitting very much heat. But actually, you know, they're still there, they're still doing things, and changes in that amount of heat they're emitting are definitely something which is an increasing field of study, which is potentially a precursor towards, volcanic eruptions, which is a very interesting area. So, so we have our sensors, and this is fantastic. Now, what we have to do then is we have to stitch all those things together. We have to, power the sensors. We have to get the data off the mountain, unless you want to walk up there and get it all the time, which, although it's interesting to do, we don't want to do all the time. So power, well, hey, I heard a few of you there thinking, oh, solar power, and you're absolutely right. Because in the deep field where we're going, then there's nowhere to plug into, so the only power we can possibly get is things like the sun's energy. And so on the top left here, this is a remote field station where they've got 3 solar panels powering all the instruments that are in that little box there. Now, unfortunately, in the winter, in somewhere like the Aleutian Islands, you often get the situation like we see down in the right here. Although, funnily enough, this particular picture I took outside my lab in New York this winter. So we had some quite heavy snowfalls, but you can see there's some solar panels there, and they're completely buried in the snow. Now, when that happens, when it does happen on these volcanoes, then the solar power is next to useless. So we need a kind of backup source of power as well. And actually, a really good one is wind. So we can have wind power. So we have 2 different sources of power which complement each other, which is excellent. Next, we need to record the data. So all our sensors are working away, trying to tell us everything they can about the volcano. And if we record it to a little computer in a box on the volcano, that's fantastic. But then again, we have to go and get the data. So ideally, we do something else. And what we can do these days is send the data via satellite back to wherever we want. So in this picture, again, of one of my sets of instruments at New York at Columbia University, there's a little square in the top of the screen there, and that's actually a satellite antenna. And that's sending all the data from my instruments that are set out there to a satellite that's sitting over Peru or off the coast of Peru, and that beams it back down to the ground and it gets into the internet. And then we pick the data up from there. So we can actually get the data from a remote field site like that, which is incredibly handy. We can also send, if we're lucky, send the data back via radio. So this funny looking thing on this site here is a radio antenna, looks just like a TV antenna, but it's inside a box to protect it from the weather. And that can send the data back to another island in the Aleutian chains, and then to another island, then to another island, and eventually back to the mainland. And then we can get some really long links, but that kind of works. So we can get data off the volcano. We can, in some volcanoes, you can even use cell phone, the cell network, but there's not that many places where you can do that. So now I think we should give ourselves all a big pat on the back, because I think we've just designed a volcano monitoring system. And, I and my colleagues can take this out to Ocmok and Cleveland over the next few years and see if we can get data so that we can try and start predicting, eruptions. Now, this is what that system looks like. Now, you just helped me develop this, and it looks a bit complicated, but it's not. If you look in the top left, you've got a seismometer, then there's GPS, and there's an infrasound sensor, some cameras, some more seismometers, more GPSs. Then there's all these little radio antennas that we talked about built into the design. And then there's this square over here is a satellite antenna. So this is what the system looks like, and when you really design a system like this. So I think we have everything we need to maybe start thinking about analyzing data. At least we have the collection system sorted out. So the question now is, can scientists really predict eruptions? And this is a big question. I know we're right at the beginning of this kind of science, really. So it's a really interesting time to be in it. And I guess the key questions are: when is the volcano going to erupt? Very handy to know. Where is it going to erupt? How big is the eruption going to be? And maybe for how long is the eruption going to last? So these are all big questions in the minds of the scientists who work on this kind of problem. historically, some eruptions have been predicted to some level, usually a very short time before the eruption has actually happened. 20 minutes in one case here, maybe a little bit longer in other cases. Where there's more information, then you have a better chance of understanding, the processes that lead up to an eruption. So, hey, so we need all that data. So that system we've just designed together is absolutely required to get us to the state where we can start to predict what's going on. So right now, on planet Earth, we don't have enough data for to be able to predict most eruptions, because eruptions in general are very rare. And so we need any data we can get to establish the normal level for a volcano. What's a normal level for a volcano? Well, I don't know, normal activity. I have a level of normal activity. Maybe you do too, Get up in the morning, go to school, or go on Zoom. Not sure where we're all at the moment. Have lunch, do more school in the afternoon, go home, have dinner, play some games, whatever, but that may be considered normal. And then if you do something different, then somebody realizes, your parents say, hey, you didn't do that yesterday, why is that? And suddenly something's different. Well, volcanoes are the same. You look for that baseline, and then you look to see what's different, and that's trying to tell us something usually. It's also very difficult to compare different volcanoes because they're all different. So the things that affect one don't always affect another one. Bit of information here. The USGS did a survey in 2004, and they established that there were 1,585 active volcanoes on planet Earth of any consequence at the time, and that less than 5% of those, or less than 80 volcanoes, and it's pretty much the same number today, I believe, are being adequately monitored. And there's a fraction of those which are places like Hawaii, which have very good monitoring, a tiny fraction, but most of them don't. So the information is still very sparse, and we really need to get systems like this monitoring system we've just designed together out there and onto the sides of volcanoes all over the planet. So if we could put our volcano system on every active volcano, suddenly we're inundated with data. You can imagine every single one of those having a satellite link, sending data back to us. And they're all coming from all over the world. And it's like, whoa, how can we process all that data? And this is where we start getting into the interesting part now, because relatively recently, these things called machine learning and artificial intelligence are everywhere around us, at least by words. And it's a type of processing that actually could be really useful, really useful to us for handling all this volcano data. I mean, what is machine learning? Well, it's basically you're taking a system and you're giving it the ability to automatically learn and improve from the experiences that it has. Sounds like to me like something out of Doctor Who, if any of you know what that is. But it's a system that works. It's it's almost a well tried and tested method now. Very recently, but tested. And it's a program that can automatically learn and improve from its experience without being explicitly programmed to do that translation into a new experience. Yeah. And that's the key thing. It's quite stunning, actually, that we can do that. So we're in this fantastic position at Columbia University that we have NASA Goddard Institute of Space Studies, NASA GISS. Columbia hosts them basically on the site on Broadway and in New York City, and their whole remit, which I'm sure our colleagues are going to tell us more about after this, is to analyze data of many types from around the planet. And climate is one of the big things that they look at. It could be anything, and this new area of volcano eruption prediction definitely be part of that. And also we have the what's called the Columbia University Data Science Institute. So if any of you are interested in data and things like that, they do huge amounts of outreach, huge amounts of education, with high schools, and it's all about learning about this sort of data science and using machine learning to analyze data and look for patterns in the data and things like that, patterns that we maybe won't see ourselves. So I'm sort of coming to the end of where I'm going to talk now. So what we have is we have the system we designed. It's out on our volcano or many volcanoes. And then we get the data comes back to our downlink. We get it back to our servers, or it can go into the cloud somewhere. Lots of choices now. And then on the back end of that, we can use machine learning to look at the processes that are going on in all that, from those sensors, from those different types of data. Look for patterns, maybe patterns across the sensors, which is something which has not been very easy to do for me. So I'm going to stop there, and thank you very much. Thank you for listening. If you need more information about our project and what we're up to this summer, do visit our website, which is avert.ldeo.columbia.edu, which Sherry can pass information on to you. And I'm Nick Frierson, and that's my email, which you can contact me on as well if you have any information. So thank you very much.
Thank you so much. That was great. And as I mentioned, we'll have someone from NASA GISS, and so we'll have Rosalba come and share some additional resources, and then we will go to answer your questions. So feel free to put more in the Q&A box. I know we already have some great ones, and I can't wait to get to them. But so take it away, Rosalba.
Thank you. I hope you can see my screen now. So hello everyone, my name is Rosalba Giarratano. I help support NASA's Office of STEM Engagement at the Goddard Institute for Space Studies in New York City. And yeah, I'm very happy to share about some supplementary resources. So today I would like to highlight Earth Observatory Kits, Infiniscope, Worldview, NASA Eclipse, and NASA Space Place. So the first resource, Earth Observatory Kits, is basically like an electronic magazine. It is created for audiences ages 9 to 14. And on the specific link that I sent you for Earth Observatory Kits, this is an issue called Sky High, Keeping Track of Volcano Plumes. And with this one, you can discover how satellites help us make air travel safer in the aftermath of an eruption. You can create your own flipbook animation and track the traveling ash and gas. And you can also see a volcano in 3D. So again, generally with this resource, Earth Observatory Kits, you can see articles and images and many hands-on activities and projects. The next resource is Infiniscope. So this is a project created by the Arizona State University's School of Earth and Space Exploration and by NASA's Science Mission Directorate. So it's a virtual space for educators and also for students to connect and to access many different, very interactive learning experiences. So the one that I am highlighting on the link is called Kilauea, and so there you can compare different types of volcanoes and the magma that is associated with them. The next resource is called Worldview. So this is a NASA app that is very, very cool, that lets you interact with more than 900 global full resolution satellite imagery layers. And many of those layers are updated daily and are available within 3 hours of observation, meaning that you can see Earth pretty much as it is right now. And so for today's topic, you could see the following layers: the volcano hazard economic risk, volcano hazard mortality risk, and volcano hazard frequency and distribution. It does take a little bit of practice to get to be able to use Worldview, but I also on the chat put the link for the tutorial. So definitely a resource that I encourage you to explore. The next resource is the NASA Eclipse. So this is a series of videos designed also for students. And there are many videos about different topics. The one that I'm highlighting on the chat is one called Slope Equation to identify how volcano was formed. So with this video, you can learn about how volcanoes play a role in how Earth looks today, and also learn about volcanoes in our solar system. And as the title implies, you can also learn how the slope equation is used to identify how a volcano was formed. And last but not least, there is this website called NASA Space Place that has online games and short videos and articles. It is in English and in Spanish. And although it is designed mostly for younger students, older students and even adults can also find many interesting things. For example, I am highlighting here the Space Volcano Explorer, which lets you learn about active volcanoes in some of the moons of Jupiter, Saturn, and Neptune. So I hope that you will also explore that. And that's it for me today. Thank you.
Thank you so much, Rosalba. So now we can look to the Q&A box. I know that Nick had already typed the answer to one of the questions, which is great. And so the first one that we have up is, how much do volcano emissions, how much are they to blame for emissions?
Well, I guess you're talking about CO2 emissions there. Now, I'm an engineer working on this project, so I know that they have quite large contribution to CO2. I don't know the exact numbers, but that is something that my colleague Einot Lev that I mentioned at the beginning of the talk, she will be able to answer that. So that's something that we can get back to answer that one on, yeah?
Great. And then additionally is it possible to trace gas emissions and check how far they have traveled?
How far they have traveled? I'd say yes, to the point where they disappear into the background. So, I mean, I know that what was our colleague from Rosalba, yeah? She was saying that they from space they can track sort of plumes, and so they can see how far they travel. When you're on the on the ground by the volcano, you can put sensors out which are seeing the gas go past, but it's actually quite difficult, as you can imagine, to track the plume itself unless you maybe flew along in it. Now, something we can do now is put gas sensors on drones. And so putting a gas sensor on a drone, which could then fly along, sniffing the air, as it were, and seeing when it was going in and out of the plume, it could actually quite accurately measure concentrations until it couldn't measure them anymore. So it will be able to tell how far these things are going. But plumes can go a long way. I mean, it's like anything, it's just got to go, it's just until it dissipates. So it depends on wind conditions and things like that around it as to how concentrated it is. Next question.
That's super neat. Yeah, our next question is, what kind of life develops inside and around volcanoes, and how long does it take for such life to emerge?
Well, again, that's kind of a question for a biologist, and this is almost an exoplanet question, interestingly, because there are volcanoes inside a volcanic vent. I mean, I don't know if this person's thinking about inside the the cone, or actually down inside the volcano. I mean, I don't know that you can get too far inside a volcano because the temperatures are so high to and sustain life. But certainly around the vent itself, temperature-wise, you probably could. But in terms of things like the gases that are emitted, I mean, there's an amazing photograph from Kilauea in Hawaii when it erupted last year or the year before now. It was the year before. We kind of lost a year, I think, unfortunately. But when this vent opened in the side of Kilauea and all this lava came out, went right through the middle of a community, a community of people living in houses. And so they had all these lovely gardens. And the lava was flowing down through that area. So obviously where the lava touched, it killed everything because it's very hot. But it was really interesting to see that in areas around where the vents were, all the life died. Basically, all the trees died, all the ferns died. You know, Kilauea, Hawaii is just amazing abundance of life. It all died because the gases are so toxic. They're coming out of this vent that even though it wasn't right in the path of the lava, there were just these areas where you could see where the wind had been blowing and everything just shriveled up and died around it. So I suspect that it's pretty difficult to sustain any kind of life inside a volcano. They're really right around the edges where you're in a tiny little area between, you know, too cold and too hot and too caustic and something, you know, and not too caustic, then life will grow anywhere, which has always amazed me. I mean, the big thing is in the ocean where you get these volcanic vents, essentially these fumaroles coming out of the ocean floor. There they get cooled down really quickly, but they cause a little warm spot, and that's where you get all these amazing life living around these just tiny little areas in the deep ocean, because the heat from the fluids coming out of the ocean floor there actually sustain life. So it's a really, you know, critical boundary as to whether life can evolve or not.
Another question we have is how many watts of power do volcanoes produce in between eruptions, and how much during an eruption?
Well, that's also a really good question. I mean, when during an eruption, I mean, I guess if you converted the amount of energy, it would be millions of watts, if you like, megawatts, probably many megawatts of power while it's actually erupting. And then in between an eruption, it's really just how much heat is emitting from the volcano in its rest state, you know, that state I was talking about where it's just doing its normal day-to-day stuff. And that would be a lot lower, but it has a big surface area. So I don't know that anyone's actually calculated that, but if you went around and, you know, I mean, when we were originally designing this system, I mentioned that we use solar power, or will use solar power and wind power to run our instruments. I did actually consider geothermal energy, thinking, well, if we stick probes in the ground, then we can, you know, we can power out, we're on the side of volcanoes, surely we can power our systems that way. The problem there is in their normal mode, it's actually not much power because you need a big temperature differential, a few hundred degrees Fahrenheit to get any useful energy out of it. And the ground beneath your feet and the air temperature are only you know, they might be 20 or 30 degrees different, but it's not very much. It's not enough to generate any useful energy unless you're right by, like that picture that I showed, whether there was two people in, you know, tinfoil suits right in the mouth of that vent on that volcano, which is a stunning photograph. There you could get geothermal energy because of the amount of heat created there is enormous compared to something like the atmospheric temperature, so you get that differential that you need to generate geothermal energy, but generally not enough to do that, I think.
Another question is the data that you transmit through radio and satellite safe? Like, can it be tampered with? How do you check its integrity?
Ah, it's a good question. And we actually have to think about that. You wouldn't think we'd have to think about it, but in today's world, we do. The satellite links are secure. What that means is that only very specific computers are allowed to connect across the satellite link. So that's one way of making security, yeah? So people can't just sort of tap in from the side and then talk across the satellite link. But that may be not totally secure. So also the data itself, we check the integrity of the data. We don't encrypt it because it's not, in fact, as soon as we receive the data, I didn't mention any of this, but we have like an open data policy. So when we receive the data, it will be stored and people can access it. They can't modify it, but they can all look at it if they want to. So we don't have any problem with other people looking at the data, but we would want to make sure the data hasn't been tampered with. And so there are built-in what are called checksums in the data. So when you collect the data, you actually have lots of little bits of data together. and the way the data, and then you can run a little program on it, which gives you a thing called a checksum. So every so often within the data, embedded in the data, and it looks like data, is a checksum. And so when we receive it, we can say, hey, you know, this bit of data that came before that hasn't been changed because the checksum is correct for that amount of data. If you do that all the time, unless somebody really knows how to get into the system, I mean, really knows, which is actually quite rare, then I think we got pretty secure data in that sense. Good question, by the way.
That's a wonderful question. I never would have thought about that. Next question is, how do you use thermal imaging to predict volcano eruptions?
Yeah, no, I didn't really talk about thermal imaging, although we will actually have a thermal camera as part of our system. One of the things they're most useful for, I mean, they can be, so you can actually look at you can look at the whole volcano or parts of the volcano with a thermal imaging camera. So you could see changes in temperature itself on the surface of the ground. And that's one way you can see changes happening. But if the changes that we're thinking are going to happen temperature-wise are going to be really small over time, like fractions of a degree, then the thermal camera may not be able to calibrate it well enough to see those tiny differences in signals. The errors in the data might be bigger than the signal itself. Yeah, and the reason for that is that although the camera may be a really good camera, you're usually a few miles away from the things you're looking at, or maybe even, you know, hundreds of meters away. But then there's an air column in between, and the air column has some effect on what the camera sees as the actual temperature. And so you have to be careful about that. But you can use thermal cameras to look at, say, the plume of a volcano, which are the gases coming out. And you may, you know, that would be more immune to, and you're not actually looking at the temperature per se then. You might well be looking at actually just how much the volume of gas coming out. But by using an infrared camera, you can see at night as well as during the day. It doesn't make any difference to that camera. It's probably slightly better at looking in poor weather at these plumes. And so you can use it in a different mode there, where you're not really using its temperature function, you're using its ability to see through, see in the night and in the day, for instance. And in the winter, that's important because somewhere like the Aleutian Islands, the nights are quite long in the winter. Another good question.
We are full with great questions here. The next one, I'm going to kind of combine a few because they're kind of the same thread, but what type of engineering did you study? How did you decide to work on volcano monitoring, or what prompted you to decide to specialize in volcanoes?
So I basically did electronics and physics as kind of a degree, yeah. And there's a lot of mathematics in there as well. So my background is in kind of that, you know, I'm a sensor designer basically. So I literally have in the past designed sensors themselves to do some of this kind of monitoring. And I've done monitoring in different environments. I've spent a long time traveling to the South Pole and the North Pole, actually, looking at changes in the states of the ice sheets there, because the sensors that I developed for those, you know, I developed for all sorts of things I could use for that sort of environment. Now, this sort of, those same sort of techniques can be applied to volcano monitoring, you know, in terms of the design of that system, you know, and sort of putting it all together and getting the data off it. And so, you know, I just think it's a fascinating area. I mean, volcanoes are incredible. Those photographs that you see, you know, particularly like Enoch's daughter standing in front of that little volcano, I just blows your mind, you know. And so I've always been fascinated by that. And so I've had the opportunity working at Columbia University in the Earth Institute and working with scientists at the Mont Observatory to get into that field. So, you know, it wasn't a specialism for me, but the techniques that I bring to that are all these different types of sensing. I don't develop all those sensors. Most of the ones we use now, we can buy basically, but, you know, the techniques I used to use for developing sensors and things gives me a big advantage, I think, for helping to develop these sort of systems.
Very cool. And you've touched on this a little bit, but we do have a question. Like, can you talk a little bit more about the team and the different disciplines of your team members?
Yeah, absolutely. I mean, so, you know, we talked a bit about the sort of engineering side, and, you know, I have a software engineer who's very good, who works for me and develops the software for collecting all this data and ensuring that it's good data and all of that. So that's one side of this kind of project. And then the other side is the, you know, the pure science side, which is the driver for the project. So the lead principal investigator is called Terry Plank, a professor at Columbia University at Lamont Observatory, and her co-principal investigator, Einat Lev, volcanologist. Now they both, that's what they study. They study volcanoes. They study different aspects of them, but they're interested in understanding, you know, the processes that lead up to eruptions. And so the whole program developed from, you know, ideas that they had about that. You know, so those are the two halves of the main part of the project, really. You know, so we come together because you can't go in the field and measure things without the engineering aspect. And then if we measure stuff, what's the use of it if we don't understand what the data means, which is the science side of it, essentially.
We have two more questions and then we'll probably cut it off there. Mercedes is asking, can you follow the volcanic activity in other bodies of our solar system? If possible, how do you measure that?
Yeah, I mean, obviously, Io springs to mind. So it's the one of the moons of Jupiter, and it's the most active body in the solar system, I think, volcanically, volcano-wise. And it's so stretched and pulled around by Jupiter's gravity field that it's just constantly has erupting volcanoes on it, and so the surface even looks kind of yellow from all the sulfur that's brought up the surface, I believe. I mean, yeah, these are also this kind of program. You know, we will work with our colleagues at NASA quite often to, you know, if we develop a technique which is particularly good at studying the way some volcanoes work, then that will feed forward at some point into maybe one of the NASA programs, building that into one of their satellite kind of programs when they send probes to, say, Jupiter. And so they would, you know, they would use that philosophy. And there's on a different program right now within the Lamont Observatory, you know, at the Earth Institute, there's a colleague of mine, and she's studying Europa. And so she's actually studying the icy parts of Europa because that's what she does. But NASA are using her data to understand what the surface of Europa might look like for when they land on it. Yeah, so they're sending probes to land on Europa and make measurements on it and things like that. And they want to know, are they going to land on a mushy surface? Are they going to sink in? Is it going to be like this? All this sort of stuff. And so she's recreating, we actually have a whole lab at Lamont where she's recreating the conditions on the surface of Europa so that NASA can understand what to expect when they get there. Now, this program, we're only just starting. You know, we haven't even got the sensors out on the first volcano yet. But when we do and move, you know, as that moves through in the next sort of 3 to 5 years, then there'll probably be, you know, feedback from that, which will then go on to things like being able to study the volcanoes on Io, so if that's what NASA wanted to do at the time.
And then our last question is, how culpable are volcanoes for warming the oceans?
Culpable? Well, yeah, I mean, geothermal energy coming up to the seafloor is there all over the place because, you know, we're floating on magma. All the continents, they're like cork floating on the magma, and then the ocean plates, if you like, they're a kind of heavier material, but they're still sitting on top of that magma. So there's geothermal energy coming through everywhere, but then that's in a state which is, I guess, and you know, I'd have to ask my science colleagues about this, but I would assume that is in some sort of equilibrium. Yeah. So the changes in temperature that we see in the oceans right now across the whole planet are due to, you know, the global warming effects of the fact that the atmosphere is warming up, and that is, you know, putting heat back into the oceans because they're a big sink for that. And so although obviously locally, you know, if a volcano erupts and it's an island, and you can imagine there's a lot of heat around that island at the time, then the local population, the local sea is going to get warmer. But then it's a local effect. And even though volcanoes are big, they're quite small relative to the whole planet. Whereas the global effects we're seeing are caused by the fact that the whole atmosphere around the planet is getting slightly warmer. It's interesting. It's an interesting thing though, because where we're going, you know, the Aleutian Islands, that's where that's where the crab fishermen go. You know, the program on TV where you see all the crab fishermen guys and these amazing seas, and it's scary as anything. Well, that's quite close to where we're going. And one of the reasons the life is so populous there, I believe, is that you get these areas of warmer sea, you know, because the sea is pretty cold near the surface, but presumably down near the bottom where you're getting this geothermal heating, it's warm enough to make a difference. And so there's more life is abundant there. But it was one of the reasons anyway. I'm sure there's other reasons, but, you know, all these things come together like that.
Wow. Well, thank you so much for coming in and speaking to us and for answering all those questions. Thank you, everybody, for asking such wonderful questions, and they were very interesting, and we're very appreciative, Nick, that you came and spoke to us, and I learned a lot. I'm sure everybody did, and I'm just shocked that, you know, less than 5% of volcanoes are monitored, you know, around, but thank you for breaking down how you can, you know, design a monitoring system for such a complex ecosystem. And so thank you so much. And these EI live sessions, they are recording, and those recordings will be shared on the Earth Institute website. So you all will have access to this, and you can rewatch it to learn even more, see, you know, and listen to all the great questions you all asked. And thank you so much, everybody, for tuning in.
Yeah, thank you, everybody. Yeah, I hope you enjoyed it. Bye.
Goodbye.